Okay, in this slide, what we have is a diagram which is giving us cutting speed for maximum productivity. And in this diagram, we can see that the cutting speed is presented against time per work part, or the time that is needed in order to produce 1 unit of the product. It has got a number of components, and those include the time for loading and unloading. This time is independent of cutting speed, so it has got a fixed value. And then there is another time component that is machining time. This time is dependent on the cutting speed. As cutting speed increases, machining time decreases. And there is another time component, and it is tool changing time. As cutting speed increases, tool changing time also increases because there is a need for more often, say, tool changes. And this curve up here is representing all these three curves in one curve, and this is giving us total time per workpiece. And as you can see, at this point right here, we've got the local minima where it gives us the minimum time per work part right here. How to get this time? We've got to make use of the equation given in the box down here. This equation is making it possible for us to compute the cutting speed, giving us maximum productivity. And in this equation, what is included is C, which is taken out from Taylor's tool life equation. Same for N, which is the tool life exponent taken out from Taylor's tool life equation. Taylor's tool life equation is also given in this slide right here. So C and N are taken out from this equation, and we have another parameter down here, which is the tool changing time. If we have these three parameters at hand, we can compute cutting speed, giving us maximum productivity. And then in the next slide, we have got a different diagram comparing cutting speed with cost per work part. Similarly, there are a number of cost components in this diagram, and those include cost for loading and unloading. When loading and unloading is in progress, we are paying someone to do the job for us, so there is a cost involved. The cost of machining time, because labor is getting paid to machine the part, so there is a cost involved. As cutting speed increases, machining time cost decreases because there is less time that is needed to produce the part. And there are two other cost components which increase as cutting speed increases, and those include tool cost, because there will be a need for a higher number of tools, and the cost when cutting speed increases, and also the cost of tool change. As more tool changes are needed, this cost component also will increase. And these four cost components are represented in this curve up here, as you can see. And then there is again a local minima for this, say, curve at this point right here. If we project it to, say, to the vertical axis, we can get the lowest cost when this cutting speed is used. This cutting speed, or V of min, is giving us the cutting speed resulting in minimum unit cost or minimum production cost. So if we want to lower the cost of production when production is in progress, we've got to make use of this one. The equation is given in the box, this equation here. In this equation, what we have included is again parameters C and N taken out from Taylor's tool life equation, plus CO, which is the operator cost rate in minute, and also tool changing time. This is what we already had, plus CT, which is the cost of the cutting tool. So if the task of us is to get the say value of the cutting speed giving us minimum production cost, this is the equation to be used. If we want to get the cutting speed giving us maximum productivity, the other equation is to be used. Two different equations for cutting speed. Okay, now let's move on to the equation sheet. In the equation sheet, we have got a number of equations, as we can see. Equation 23.1 the top equation up here is the one making it possible for us to compute the theoretical value of surface roughness. And this is a function of feet and also tool nose radius. In turning, we had experimented this in the workshop environment. When the nose of the cutting tool changes, it will have an impact on the resulting surface finish. So this is representing the geometry of the cutting tool, and of course feet has a great effect on the resultant surface finish. So theoretical value of surface finish can be computed by this. However, in practice, we may achieve a surface that is rougher than Ri, and this is represented by Ra, actual surface roughness. Why is it rougher? Because in practice, there is a vibration of the machine tool, and also there is imperfection in the workpiece material, cutting tool, etc., which also deteriorate the surface roughness that is computed in or estimated in theory. In order to relate the value of Ri to Ra, we've got to take the value of Rai into consideration. That is the ratio of actual to theoretical surface roughness. How do we get this value? We get this value from this diagram here. In this diagram here, as we can see, if we have the value of cutting speed at hand, the cutting speed is presented in, say, in the horizontal axis right here. And this is indeed representing the vibration of the machine tool as well when operation is in progress. If we have the value of cutting speed at hand, and if we know the type of the material, one of these three groups should represent the type of the material. Those include free machining alloys, cast irons, and ductile metals. If we know the type of the workpiece material, we make use of the right curve, and the intersection of the cutting speed and the given type of the material will give us a value in the vertical axis, and that value will be sitting in equation 23.2, making it possible for us to relate to make use of the theoretical surface roughness and get the value of the actual surface roughness. Now let's explain this by making use of say an example problem. Well, problem one, a part to be turned. So we know the type of the operation, and it is a turning operation as explained here. In an engine lathe must have a surface finish of this one. Surface finish or surface roughness are both used in the industry in order to represent the quality of the surface being machined. So the surface roughness is 1.6 micrometer. That's what we want to achieve. The part is made of free machining aluminium alloy. Cutting speed or V is given. So we know the value of V, and that is equal to 150 meters per minute. Depth of cut is also given 4 mm. Nose radius, NR, is this much. So we know the value of nose radius or NR, which is equal to this much. And then determine the feet that will achieve the specified surface finish. We've got to compute the feet value of F, which gives us this value of surface roughness in a turning operation. This is what we need to do. In order to compute or determine the value of feet, what we need to do is to make use of the two equations given in this slide here. Well, first we compute the value of Ri from here, and once we have the Ri is given, NR is given, first we've got to compute the value of feet from here. What we are provided with is the value of Ra. So let's see how we can convert the value of Ra to Ri, and then we take the value of Ri from here and make use of the first equation to get it done. In order to do the conversion, if the value of Ra is equal to 1.6, that is given in the statement of the problem, we need to get the value of Rai out. In order to do this, let's take a look at the diagram. The given value of, say, cutting speed is 150. Where is 150? Well, if we take a look at the horizontal axis, we can see that the value of 150 is outside. It's somewhere here in the diagram, which is outside the diagram. And the type of the material is this one. If we continue this curve, it will go somewhere at 1 or below 1. So it is safe to consider the value of RAI to be equal to 1 for this given problem because it is outside of the diagram. So we consider RAI to be equal to, say, 1 for this given problem. If the value of RAI is equal to 1, what can be concluded is that for the given problem, RA, actual value of surface roughness, is equal to the theoretical value. In reality, it is not the same, but it is very close to. So the difference is negligible, so we just ignore it. And then we make use of the equation on the top in order to compute the value of F. Ri is equal to 1.6 and Nr is also given. So it will not be hard to substitute the values and then get the value of F computed. If we have the values of Ra and also the values of Ra and also the value of F at hand, then we can easily compute Nr and RA are given. We can easily compute the value of F, and that corresponds to 0.196 mm. So if we make use of a feed of this much for this given operation, the resulting surface finish will be 1.6 micrometer, and that's what we need. Any questions on this? Okay. Now in part B, it is asking us to solve the problem. If cast irons are used instead of aluminum and the cutting speed is reduced to 91.5. So let's do it this way then. Then if this is the case, what we have is a cast iron as the material and cutting speed 91.6. Cast irons are represented by this curve, the middle curve, and also cutting speed is this much, 91.5. What we need to do is to get the value of RAI for this given cutting speed and also this curve. So it comes to this point, the intersection, and then we've got to bring it to here, which comes to a ratio of 1.3. Now the ratio of RAI is 1.3, which is relating RI to RA. So we need to do the problem again, and for doing the problem again, that's the way of doing it. Now we know that RAI is equal to 1.3, and now we can establish a relationship between actual surface roughness and theoretical surface roughness, which is this. Now if we substitute the values of surface roughness that is given and also nose radius that is also given, then we can easily compute the value of feet, and that corresponds to 0.172. So as we can see, this feed is now less than what we had computed for aluminum, because aluminum is a type of free machining alloy. It can be easily machined. So with a higher feed, we can achieve the same surface roughness. When it comes to cast irons are generally harder than aluminum alloys, and it is more difficult to machine them. So with a lower feed, we can achieve the same surface roughness, and this is evident from this problem. Okay, is there any questions? No questions. Okay, moving on. Moving on to the next problem. Well, in this problem, what it is asking us to do is, well, for doing this problem, we've got to take a look at the rest of the equation sheet. These equations, have I explained these equations since you joined, Paul? Okay, I have. So we make use of the equations that are given in here for doing the second problem, this problem. What is it asking us to do? It is asking us to do this problem. A high-speed steel tool is used for turning of steel work part. The dimensions of the workpiece are given. the length is 300 mm and diameter is 80. So dimensions of the cylindrical workpiece are given. Parameters of the Taylor tool life equation are also given. N and C are given. If we make use of a feed of 0.4 mm per revolution, feed F is given, and then the operator is receiving a wage of $30 per hour. The operator is receiving this wage in order to perform the machining. This is equal to CO. CO is also given. Tooling cost per cutting is given. For each cutting edge, we are paying $4. It takes 2 minutes to load and unload the workpiece. TH, the time for loading and unloading, TH is given, that is equal to 3.5 minutes. 3.5 minutes is the time for loading and unloading of the workpiece after the part is produced. In part A, we are to determine the cutting speed, or V. Cutting speed is to be computed, which is giving us maximum production rate. Cutting speed for maximum production rate, or V of max, is to be computed, and also the corresponding tool life in minutes is to be computed. So some information is provided, and on the basis of the information that is provided, we are expected to compute the cutting speed and also the corresponding tool life. Let's take a look at the equation sheet right here. We have got a number of equations here. We've got to see which one of the equations is the one to be used. For this given scenario, there are 2 equations for cutting speed, and those include this one and also that one. Which one is the one to be used for this problem? We've got to compute the cutting speed giving us maximum productivity. The one at the bottom is giving us the cutting speed for minimum cost. So it is equation 23.7. That is correct. This equation is the one to be used. This one right here is the one to be used for this given problem, because we are after the cutting speed giving us maximum production rate. So we take this equation out from the equation sheet, and in order to compute the corresponding, say, tool life, we've got to make use of the Taylor's tool life equation, which is not listed in this equation sheet. This is something that we had in the previous lecture's equation sheet. We take that one from there as well. Okay, let's get back to the statement of the problem. So if we take this equation out from the equation sheet, this equation, we can make use of it. However, please note that the operator's wage is given in dollars per hour, and we've got to convert it into $2 per minute before we can make use of it. So it's easy. We divide it by 60, which is giving us $0.5 per minute. This is the wage of the operator per minute. And then we make use of the equation for cutting speed. This will be used later on. Indeed, this parameter that we have computed will be used later on in the second part of the problem. The cutting speed, for cutting speed, what we need is the values of C and also N, and these values are both given up here. Up here we have got the values of C and N, and also TT. What is TT? The tool changing time. Tool changing time is also given. It is tool changing time. How much is it? It is 3.5 minutes. The time needed for tool changing is 3.5. So we substitute the values. 3.5 is sitting there, the values of N and also C all in the equation, and this results in computation of the cutting speed giving us maximum production rate, and that is 49.8 meters per minute. Okay, and then we take the equation for tool life, that is Taylor's tool life equation, from the equation sheet that we had in the previous lecture. We take this equation out from there. If we have the value of V, which is just computed, the value of V is 49.8. Values of N and C are all given in the statement of the problem. So we rearrange the equation for T, substitute the values of N, V, and also N, everything in this, which is giving us the tool life for this given problem. And that comes to 23.42 minutes. So this is the, if we make use of this cutting speed, then this will be the expected tool life for this given problem. Okay, any questions on this? No questions. Okay, let's move on then. And then in part B, we are asked to compute the cycle time and cost per unit of product. Now let's get back to the equation sheet again. This is the equation sheet. We are asked to compute, say, cycle time up here. If we take a look at the equation sheet up here, we have got an equation giving us the cycle time. If we have the values of tool changing time, machining time, and also workpiece changing time, machining time, and also tool changing time at hand, then we can get the value of cycle time right here. We take this equation from the equation sheet. And then what else we need to do? We are also asked to compute the cost per unit. So we take another equation out from the equation sheet, and that is this equation. So we take the equations 23.3 and 23.11 from the equation sheet. In this equation, what we need to have is the wage of the operator, which is CO. We already have that. TM is not given. We need to compute TM machining time. TH is already given, so TM is not. We've got to compute that one. And also the cost of the cutting tool CT is given. So if we have this equation, I thought the only parameter that is to be computed is TM. If we compute TM and also NP, what is NP? The number of parts that can be machined by making use of the same cutting tool. This also can be computed. We need to compute NP and also TM in order to compute the unit cost. And for unit time, we need to compute TM and also NP in order to do the problem. Now we take these two equations out from the equation sheet and get back to the statement of the problem, problem 2. Okay. Now we do the computation of machining time. Machining time equation, this equation is the one that was covered in the previous lectures. This one is the one that was covered in the one of the previous lectures when we discussed different types of machining operations. In there, we also had this equation included. So we make use of the equation for, say, machining time for turning operations. In this equation, what we have is the diameter and also the length of the workpiece, and these are all given. And then feed and also cutting speed. These ones are also available. F is given, phi is just computed up here. So we have got phi, V computed up here, F is given, which is speed, D and L are given. So we have everything in order to compute the value of machining time. This is the time of machining, excluding loading and unloading, excluding, say, tool changing time. However, loading and unloading is also given, and tool changing time is also given. Now, the task of us is reduced to computation of NP. What is NP? The number of parts that can be machined by making use of the same cutting tool. Please note that we have already lifetime of the cutting tool at hand. Each cutting tool lasts for 23.42 minutes. If we have the value of machining time at hand, this one, it takes 3.787 minutes to machine one unit of the part, and cutting tool lasts for 23.42 minutes. So if we divide this value by this, then it gives us the value of NP, and that's what we do. We divide 23.42, which is tool life, by the time that it takes to machine one part. It is making us able to produce 6.184 pieces by making use of each cutting tool that is considered as NP. We can round it down to 6. So we round it down to 6. Each cutting tool can machine 6 work pieces. Now we have everything at hand. We compute the value of cycle time, which is this much. And then we move on to the next part of the problem, cycle cost. For cycle cost, or the cost of producing one unit of the product, we need to pay the worker to or machinist to machine the part, which the rate is already given. We converted the rate from dollars per hour to dollar per minute. So the dollar per minute figure sits down here, times cycle time. Cycle time is just computed. So it takes into consideration all the times when operator is getting paid, including machining time, tool changing time, and loading and unloading time. All are included in this, plus the cost of the cutting tool. The cost of the cutting tool is this much. It has to be divided by the number of parts that are produced, and this is already computed. So we have got this at hand. So we can easily compute the cost of the producing of 1 unit of the workpiece material. That comes to $3.85 per piece. And that's what we needed to compute in this problem. Okay, any questions on this? No questions. So let's move on to the next problem, problem 3. Problem 3, what is it asking us? Solve previous problem, except that in part A, determine cutting speed for minimum cost. How does it change the problem? The way that we do the problem is exactly the same, except that the equation that was used to compute cutting speed will be different now. The equation that we used in order to compute cutting speed, let's move on to the equation sheet right here. Okay, the equation that we used in order to compute the cutting speed in problem 2 was this one. The cutting speed giving us maximum productivity. Now we want to compute the cutting speed that is giving us minimum cost. So instead of this equation, we move on to this equation down here. Equation 2313 will be used this time. And in this equation, let's see what is to be included. C and N are the values that are given. CO is the rate of the operator. This is already at hand. TT, tool changing time, is already at hand. And cost of the tool, CT, is already at hand. So we have got everything to get it computed. So we take this equation out from the equation sheet. That's the only difference between problem 2 and problem 3. Now let's get back to problem 3. And okay, this one. So we take this equation out from the equation sheet and do the computation of cutting speed, which comes to this much. Do we expect the cutting speed giving us minimum cost to be higher or lower than the cutting speed giving us maximum productivity? The cutting speed giving us minimum cost is expected to be lower than the cutting speed giving us maximum productivity. Now let's take a look at this figure. The cutting speed giving us minimum cost is 42.6. Let's compare it what we had in the previous problem. In the previous problem, it was 49.8, which is, as we can see, the cutting speed giving us maximum productivity. The cutting speed giving us maximum productivity is 49.8. The cutting speed giving us minimum cost is 42.6, which is lower, and this is reasonable. A lower cutting speed is giving us a longer tool life. Now let's take a look at the tool life. The corresponding tool life for this cutting speed is now much more than what it was before. In the previous problem, we had it computed 23.42. Now it is increased to 76.96. There is a small difference in cutting speed, but there is a big difference in the resulting tool life. So the tool life is extended to 76.96, roughly 3 times greater, less than 3 times, but close to 3 times greater tool life is achieved. And this will affect everything. Now we do the computation of, say, TM, which is machining time, as well as cycle time for this given problem, which is now different. Now cycle time, cycle time is more, and also the cost of machining is less. It's now the cost of producing 1 unit is $3.55 per product. How much was this before? Let's get back to the previous problem. It was this much, 3.85. When productivity is the objective, the cost of unit production of each unit is more. When economic production is actually objective, then the cost of producing each unit is less, and that's the difference between the two. Maybe the difference is not much in one unit, but when you are doing this all the time, from the morning to the evening, on a daily basis, on a weekly basis, in a monthly basis, it makes a big difference. Even a fraction of a cent makes a big difference. Now it is about, say, 20 cents or so, which is the difference. It's about 30 cents is the difference, and that makes a huge difference in the end of the year. So depending on our policy, we choose the right cutting speed, and it will affect everything. Any questions on this? No questions. Okay, let's move on to the next problem. Well, in the next problem, we've got different types of cutting tools that are used. Let's just explain briefly what this type of cutting tools are. In here, we have got two different types of cutting tools. On the top, we have got brazed cutting tools, these ones. As you can see, the tip of the cutting tool, which is the cutting the material, is brazed or welded to the tool holder or to the shank. And then this is a permanent type of the joint. We do the cutting, and when the cutting tool is not sharp enough, it gets blunt. We've got to subject the cutting tool to a regrinding operation in order to make it sharp again and reuse it. And we can do this a number of times. After a number of times, then we've got to replace the whole cutting tool with another one. So there is a cost of grinding that is taken to be consideration in doing the computation of the unit cost, if this is the type of the cutting tool we are using. And this is also a milling cutter, where we have got the cutting tips that are brazed to the actually shank or to the holder of the say cutting edges, and this is also the type of the cutting tool that is used in milling operations. Again, the type of the joint is permanent, so when the cutting edges get blunt, we've got to subject the cutting tool to a regrinding operation in order to resharpen the cutting edges. And in contrast with this, we've got, say, carbide inserts that are used in the images at the bottom. As you can see, there is a certain mechanism for tightening the insert onto the holder of the insert. And each of the inserts have got a number of cutting edges, so that when one cutting edge is blunt, then we've got to index it and bring the other sharp cutting edge into position in order to take the cutting. So these are the disposable cutting edges, and we've got to dispose them once they get blunt. So the type of the cutting tools are different, and the process that is to replace the cutting tool will be slightly different. So we've got generally two different types of cutting tools that are either brazed cutting tools or carbide inserts that are disposable ones. Okay, now let's move on to the next problem. What is this problem asking us to do? Compare disposable and regrindable tooling. So the ones that we have just discussed in the previous slide. The same grade of cemented carbide tooling is available in two forms for turning operations in a certain machine shop. Disposable inserts, the one that I had discussed in the previous slide, and also brazed inserts. Both of them were shown in the previous slide. The parameters in Taylor tool life equation for this grade is given. So we've got N and C for this type of the cutting tool material. Under the cutting conditions considered here, these are the values of N and C. So machine time on the lathe costs $24 per hour. So this is the cost of running the machine machine tool. The work part to be used in the comparison is 375 mm long and 62.5 mm in diameter. So the dimensions of the workpiece are given. The time for loading and unloading is also 2 minutes, and the feed is also given, which is equal to 0.3 millimeters per revolution. Now, for disposable inserts, the price of each insert is this much. The price of each insert is given. There are 4 cutting edges per insert. So we've got a type of insert with 4 cutting edges. And the tool changing time is also given to be equal to 1 minute. Now, for the other type of the cutting tool, for the brazed insert, the price of the cutting tool is $30, and it is estimated that it can be used 15 times. It means that we use it once and then we do 14 times of regrinding and resharpening in order to use the same cutting tool. And then we've got to replace the whole cutting tool. The change time for the regrinding, tool change time for regrinding is 3 minutes. So every time we're spending 3 minutes in order to replace the cutting tool. The standard time to grind or regrind the cutting edge is 5 minutes. The grinder is also gets paid by this rate, $20 per hour. For regrinding, we've got to pay the person who is doing it, and the rate is this much. Now, for the 2 tooling cases, compare A, cutting speed for minimum cost and tool lives, and B, cycle time and cost per unit of production. These are the ones to be computed, and then we've got to decide which one of the cutting tools is the one that is working better for us, and we've got to recommend that one. In order to do this problem, the way that we do the problem is similar to the previous problems that we had, problems 2 and 3. What we need to do is to take the right equations from the equation sheet and do the problem exactly the same as what we did for the previous problem. So we take a look at the equation sheet and take the value, we take the equation for cutting speed giving us minimum cost out and substitute the values, and then it gives us the cutting speed resulting in, say, minimum cost for the first scenario, which is making use of the disposable inserts. We make and then we compute the corresponding tool life, which comes to this much. So we can get this computed for the disposable inserts, and then we do the computation of the cost and also cycle time for this given scenario. When disposable inserts are used, say cycle time is this much and also unit cost is this much. These are all computed. Now we need to repeat this for the second scenario when we make use of the regrindable tooling. Again, same equations are used. However, when the equations for this scenario are used, we get different values for cycle time and also for the cost of producing 1 unit. And as you can see, these values are now different. Now the recommendation. Now we've got to take a look at the problem solutions and compare these values with one another. Where we make use of the disposable inserts, then the unit cost is this much. When we make use of regrindable inserts, then the unit cost is that much. Which one is lower? That is very obvious. When we make use of disposable inserts, then the cost of producing 1 unit is less. So this is the one that works better for us. So we stick to making use of the disposable inserts. When we are regrinding the inserts, we've got to pay someone for regrinding, and the cost of regrinding is also affecting the unit cost, which is this much. So it will be more, and it is better for us to stick to the first scenario. Okay, any questions on this? How is the cost of grinding taken into consideration? If we take a look at the equation sheet, let's get back to the equation sheet right here. Here, in the equation sheet, equation 23.1 is the one that is taking care of the regrinding cost. Let's see what is in here. In this equation, we've got the cost of insert divided by the NE, and NE is the number of cutting edges, and then we've got also to consider the time of grinding times cost of grinding, and this information is given in the statement of the problem as well. So we make use of this equation in order to compute the cost of tool when regrindable cutting tools are used. However, in the case of disposable inserts, the cost of the insert is directly given. So for the case of regrindable cutting tools, we've got to make use of equation 23.10 in order to get the value of CT. And that is what was taken into consideration in the problem that we just considered right here. Right here, in order to compute the value of the insert, we've got to make use of equation 23.10 in order to get the value done. And that is computed right here. Right here, you can see the cost of the insert is computed, which is taken into consideration. And how is this taken into consideration? $30 is the cost of the insert, and it is used 15 times. So we divide it by 15, which is giving us the cost of the cutting tool, which is used once. And then this is also taking into consideration the rate of the operator who is doing the grinding. That was given in hours, and we've got to divide it by 60 to get the rate in minutes. And it takes 5 minutes in order to do each time of the grinding. So in here, the cost of regrinding is also taken into consideration. Okay, that's it for today. Is there any questions on this? No questions? Okay, that's all for today. Make sure that you practice on all these problems and do the problem in your own time. And thank you so much for your participation. Okay, that's all for today, everyone.